everyone. What we have here is a battery under an ice pack. So we have cooled this battery down to 8 degrees Celsius, so 7-8 degrees Celsius, and we want to simulate a battery that's operating under cold wintry conditions to show you how the battery's performance can degrade as the temperature goes lower. We have the battery hooked up to a battery tester, right? So we have a battery testing device right here, and it's reading off the data as it loads up the battery with a resistive load. It will plot on this chart the discharge curve. So let's go ahead and start the discharge. There you go. So what we're doing, our starting voltage is 37.35. Under load it's 13 amps, right? So we are discharging 13 amps as we go. Now you have the two curves, right? The blue one is the discharge curve, the current discharge curve, and the red one is the 13 amps constant, right? It's the load curve. The load, right? That's the load. So we will see in about half an hour how much discharge, how much the performance is affected by the low temperature conditions that we are subjecting this battery under.
Below nominal.
Okay, so it's been barely a minute, and you can see that from the full charge of 43.45, it dipped off the cliff, you know, and almost to a 37.8 volts here, and it, you know, goes down, and it's cut. It's cut. It's done. Less than a minute. Hey guys, we are subjecting the battery to so-called winter conditions, so low temperature conditions at around 9 degrees Celsius, basically sub 10. Alright, so we have been cooling this pack down for about half an hour, right? And this one, our probe reads about 9 degrees. So, and we are discharging, right? Just now we are discharging at 13 amps, but now we are discharging slightly lower at 8 amps. So because we found that the drop was too drastic and it really cut off prematurely. So we started at about 41 volts. Alright, we started at about 41 volts, and we are draining out 8 amps. So let's see how the discharge curve based on this resistive load will perform. Okay, it's 12 minutes later. So let's check the temperature. Oh, it's actually increased to 18 degrees. Mostly because as it's discharging, actually warms up the entire pack. So the heat from the cells, I mean, actually warms up the entire pack. You know, so from a sub 10, it's increased in temperature to about 18. And let's look at the discharge curve. Okay, so we have been discharging for about 12 minutes here, and it is down to, the voltage is down to 37 volts, right? So it cuts off at 37 volts under an 8 amp load. So, and it was able to run for 12 minutes. We will analyze these curves a bit later. Now let's get the temperature of the battery up to a normal room condition environment, and then we'll show you, we'll run the same discharge load, and we'll see how it performs under the same conditions. So we have fully charged the same battery pack, and at room temperature it's 27 degrees Celsius, right, because there's no winter around here. So it's at room temperature 27, and we are going to run the same test at, so the full charge is 42.84 volts, and we're going to run it at 8 amps. So let's go ahead and do that. Okay, so the fan is running because the load resistance is kicking in, and so you can see it's running at 8 amps, and there you see the dip. Okay, we're not running at 13 amps like before because the dip was just too much. It didn't really prove to be a conclusive test. So we are just running at 8 amps right now. You can feel the battery is getting hotter as the discharge across that load being activated right now. Okay, so we'll wait for a couple of minutes and then we'll check back. Alright, it's been about 11 minutes as the timer says. We are still drawing 8 amps consistently, as you can see from that red curve. And with the blue discharge curve, you have it down to, it's at about 34.15 volts. Alright, it's still stable. Okay, and the temperature has risen to 30 degrees Celsius, which is normal because it's discharging and it generates heat when it discharges. It's at 11 minutes and, oh, it's at 12 minutes in fact. So as the timer says, 12 minutes, so we're still waiting for it. So it has already exceeded the capacity when the battery was running at sub 10 Celsius. So it's looking like it's gonna perform better right now, but let's check back in a bit. Alright, so we are at 15 minutes and it just cut off. The battery has reached its lower cutoff point. And so we are at 32 degrees. That's where the battery has heated up to. So let's look at the curve. It is at 34.15 at the lowest cutoff point with a discharge of 15 minutes and 16 seconds. That's pretty good. We started out at 42.9, I think. And now we're at 34.2, so that's a pretty good discharge curve. Okay guys, so for the last step of our experiment to see how current discharge of battery is affected by the temperature, we have a box of dry ice here where we've inserted the same battery we've been using all this time. It's fully charged up to 43.9 volts, right? It's a fully charged battery we've inserted into dry ice, and we are trying to get the temperature down to about -10, right, between 0 to -10 degrees to simulate an actual winter condition, right? Since we are in the tropics and we cannot, get that sub-zero temperature here. So we have this box of dry ice. We have got the temperature probes on the battery, one on the heating element. So if you look up for our experiment, the T3, right, is on the part where the heating element isn't, so it's on the battery. So T3 is on, the T3 probe is on the battery. Okay, went to sleep. Okay, so the T3 probe is on the battery and the T4 probe is on the heating element, which we are going to show you if we open it up. Okay, let me just show you real quick how we set it up. Okay, so temperature is dropping. Temperature is dropping. The reason why T4 is sub-zero, reached sub-zero faster, is because this is directly in contact with the dry ice. Okay, so this is the same battery. We've got our heating element up. Okay, and we have our dry ice right here, very close. It's not exactly touching onto the probes, but it's very close to the battery. Okay, so this is how it's set up. So a little bit of education for everyone, including us, because we have never operated in a sub-zero condition before, and I thought it would be fun if we could do this experiment. So all we're doing right now is to wait for the T3 to actually go into a sub-zero state. And hopefully it does, because there are many gaps here which will be hard for us to seal up. Okay, it's dropping, you can see very nicely. Just want to make sure that we'll start the experiment, we'll start the discharge the moment T3 gets to about -5 or so. Hopefully we will get there. T4 is at already -8. That's because the copper heating element will probably cool down the probe faster than the other probe, which is on a plastic shell. Okay, so we're back. The temperature has fallen close to 0 on one probe, and then it's -10 where it's closer to the ice on the other probe. So I think it's a good time to start. So let's do this, right? First we're gonna discharge it without the heating element on, and then after that we'll discharge it with the heating element on. Okay? And then we'll compare how the two curves match up. So let's take this. Right here. Right, connect it up. Okay, we want it to be part of it outside. Okay, so the whole time we're going to measure the temperature. And we seal it up with our super high-tech tape. We are starting at 42.24 volts, and we're going to be drawing 8 amps constant, just like the previous test. And the current discharge curve is just going to be plotted out. Right now we are sub-zero on both probes, so let's go ahead and start the experiment. Okay, so as we see, the red curve is the discharge, is the load, so it's 8 amps drawing, and the blue curve is the discharge curve. It's straight away right off the bat, it dipped about 4 volts or more actually. Well, sorry, about 3 point something volts, close to 4 volts. And right now it's really diving. It's really diving hard. It will cut off very soon because the cutoff voltage is about 32 volts. And at this rate you can tell that it's going to cut off within less than 5 minutes. Where previously, when we were running it in non-sub-zero conditions, it took at least 12 to 15 minutes to fully discharge to 32 volts. But given this rate, we're only 1 minute in, we're at 33 volts. It is going to be very fast before it hits that lower threshold. Okay, the steepness of a curve is in stark contrast to what we've seen before in room conditions. Stopped. See, the moment it stopped, the voltage starts climbing up again, right? So that happens for lithium-ion batteries that are operating in very cold conditions. The voltage sag is very high. The moment that current is being drawn out, the voltage will drop drastically to where the lower limit is hit, such that the whole battery, the BMS, would shut it off, because BMS normally has a protection feature where it prevents the entire voltage of the battery from going undervolt. Alright, so for the last part of our experiment, what we're doing right now is we're fully charged the battery again. So right now the full charge is, okay, so it's plugged in, and we can see here it's 42.75 volts. Okay, that's just about right for a 36 volt battery. And we have plugged in the thermal heater, and it's showing here. Okay, so T3, the probe, is connected to just a normal plastic string wrap surface of the battery, and this one is connected to the heating element, which is showing 45 degrees. That is perfect. Alright, that is perfect. So we are going to wait for this to come down to close to 0, just like the previous experiment where we had it about 0. Bam! Okay, so if we look inside, that's the heating element and it's connected right here. Okay, and let's see, where's our probes? Okay, T3 is on the battery surface and T4 is on the heating element. We'll wait till the T3 drops to 0 or sub-zero before running our discharge experiment. So what we like to do right now is we have shown you what the inside looks like. Right, we haven't connected the heating element, but we will as soon as we get the desired ambient temperature. And if we don't get there, sub-zero conditions, hey, you know what? We've got some spare dry ice that we can still dump into this little styrofoam box. Alright, finally, after dumping that whole 1 kilo of ice into the bucket, into the box, we finally got a sub-zero condition. So let's begin our experiment. I will have to remove the lid so that I can connect the heating element to the battery source, and then we will run the discharge tester and plot the discharge curve on the computer. Okay, so we're going to connect this to a power source to the heating element, and then we are good to go. Okay, so once the heating elements are connected, let's look at our thermometer. Straight away you can see the immediate effect of this. Okay, so it's still climbing on the probe that's on the heating element, but climb isn't so fast on the other probe that's not on the heating element. That's normal, right? That's just to tell us what temperature the heating element is heating to, and this is what the rest of the battery is heating to. Okay, but it has slowed down the climb for the battery, so that's good. Alright, so what we're gonna do is we are going to run the discharge. Okay, we're gonna run the discharge at so right now, just for record keeping, it's at 42.46 volts. That's normal because we are also running the heating element off the same battery that we are discharging. Okay, so we're gonna start it. There you go. Hear the fan running. Right. See the curve shooting down. So that's going to be a very quick test. It won't take long before it actually hits the lower limit and cut off voltage. Okay, that's the end of our run. That was really fast. You can see it dropped off a cliff at around 34 volts. Right, it dropped off a cliff and that's it. Went to 0. Okay, so there's something interesting I want to point out. As with discharging a sub-zero battery, right, where the discharge just falls off the cliff, or it just discharges very prematurely or rapidly, where it just discharges very rapidly, the same can be said of charging. So the charging curve for a very cold battery, close to 0 or sub-zero, is that the battery is going to charge up to a suboptimal limit, upper limit, right? So this is a 36 volt battery, and you would expect the battery to give you about at least 42 volts of charge at full capacity. Now the problem with this sub-zero battery is that it is only charging to 40 volts. So at 40 volts, what you're getting is suboptimal. What we did is we connected the heating element, and the moment it is warm to room temperature, right now it's just slightly cooler than room temperature, it's able to start charging again, hopefully to 42 volts this time. But what happened just now is when we took it up from the ice bucket, it was only able to charge to 40 volts, and that's it. Hey guys, okay, we are back with our fourth and final experiment, and we have the battery with the heating element inside this box. It's got dry ice packs all surrounding it, and right now we are getting a sub-zero rate which is ideal. Yes, that's exactly what we want. So we've got two probes now. Sorry, we've got three probes. Two probes. The first two probes are measuring the left side and right side of the box. So those are the environment probes. And then we have our fourth probe here, our third probe here, which is on the battery exactly, right? So this is our battery probe, and then the other two, the sub-zero ones, are the environment probes. So what we're going to do is we're going to discharge it the same way we did with our previous batteries at the same conditions, under the same conditions. So right now it's 42 volts. We're going to discharge it at 8 amps, and the cutoff voltage will be 32 volts. Okay, and we'll see how that goes. So what we've done differently here, the only thing we've done differently is we've added something new. We've introduced, in our previous experiment, we had only the heating element wrapped around the battery in direct contact with the cold environment. Now this time we've added a material such that it would retain the heat better, and it will help the battery to operate within a heated environment by retaining the heat much better than previously. Right, so we are going to start this experiment right now. Okay, so discharge as we speak. So you'll see the voltage set right off the bat. This voltage set is going to cause the battery voltage to drop from a 42 volt to a 30, I would say around 39 to 40 volt condition. And then it's slowly dropping. Let's look at the temperature. The temperature is at 22, which is not bad. That's ideal because the heating element's on. So 22 is actually a good temperature to run at. Of course, in the ideal operating environment, we want the battery temperature to be around 25 to 40 degrees. So this is fairly close, and this is really good. So that means our material is actually retaining the heat pretty well. So you can see the discharge curve is relatively linear, which means that the battery cells are stable and they are behaving predictably. Okay, so from a voltage of 42 volts, it dropped to 37 within the first minute or so. That is entirely normal because firstly we have the heating element running off the same battery, so do remember that it will actually draw out a bit more current than a normal operating scooter on this 36 volt battery. Now the other issue is that in the cold environment the discharge is actually going to be steeper than in a room temperature or a heated environment. Okay, at the 4-minute mark we are looking at our temperature climbing on the battery to about 24 degrees, which is perfect, right? The heat from the battery discharge is retained within the battery environment, hence warming up the battery itself. So which is ideal in a winter condition where we want to use the battery's heat to actually warm the battery, warm itself up. Right, the outside ambient temperature is still sub-zero. Right now we are at 33 volts. We are almost there in terms of the cutoff. It's very close and we're running past 10 minutes. So it's extremely ideal because in the previous experiment, if you remember what happened, where we have the exposed battery in contact with that cold environment, the sub-zero condition environment, it actually collapsed. The voltage just collapsed after about 2 minutes of runtime. So we're not seeing that right now because we are able to control the heat in a way that the battery is heating itself up, and with that external heating element source, it's actually creating a very ideal condition for the battery to run. Oh, okay, you can see a slight dip in the curve. That's when you know the battery is about to die. You can see a slight dip here. That happens when it's reaching its lower limits of what the cells can take. Okay, so anytime now, we are running at about 12 minutes. Bam! Okay, there you go. Okay, So it's cut off, it's perfect, it's total runtime of 12 minutes. So don't forget, we are still running with the heating element on. Now if we have a switch where it's able to turn the heating element off at a certain temperature of about say 30 degrees or 25 degrees even, and just let the battery's temperature take over, the heat generated from the discharge take over, we could actually extend, oh now the fan is off, so we could actually extend the runtime to maybe 15 minutes without that current pull from that heating element. So, and you know, prior to the start of this run, we actually also warmed up the battery a little bit for about 2 to 3 minutes, so it actually put some current to this run. So all in all, actually it's a pretty good experiment, because running with the heating element and simulating a scooter runtime of 8 amps, it is able to do 12 minutes of a run. So that's pretty good. Let's open up the box. Okay, let's open up the box, and then we would review what we did to the battery. Okay. There you go. This is our battery. Alright, forgive the graphics here, but what really this is actually just a mouse pad. Okay, this is what we call a neoprene mouse pad. Now, neoprene, as many of you may know, is used on wetsuits, diving suits, and a whole variety of industrial functions like cable wrapping and hose binders. So this is a mouse pad that we have wrapped the battery around. So this is, but it isn't just this neoprene. Okay, let's say if we were to remove. Okay, let's open up and see what it is. Okay, and voila. Okay, 2 heating coils, one top and one bottom, connected straight into our battery. Of course, there's a switch, right, which is right here, right, a DC converter, and ideally a switch, right, so you can turn off the heating element whenever you want to. So we have got this wrapped around this neoprene blanket, and that's what keeps the heat in, so your battery would stay at the ideal temperature of 23 to 40 degrees. Okay, so in a real life situation, say for the 010X, all you need this neoprene sheets. Alright, if you're a fan of PUBG, you can get one of this PUBG printed neoprene sheets. These are very thin sheets. This is probably less than 2 mm thick, or probably 2 mm thick. Right, lay one on top of the battery, and lay one below the battery where it touches the aluminum. I think that's as good as you can insulate it. So with just one sheet on top and one sheet below, you can get pretty good heat retention within the batteries itself. Okay, so that is one way to implement this heat management system in your scooter in a real world condition. Any more questions, just let us know. Drop us a comment, drop us a message, and tell us, hey, did we miss anything? Is there something you'd like to know? Is there something you'd like to play with? We will try our best to accommodate you as best as we can, but if not, that's the end of our experiment. There will be no product associated with it, something that we can't test in real life. We are in the tropics and we do not have anywhere close to 10 degrees Celsius temperature, so this is as good as it gets in terms of coming up with a good solution for cold weather riding. So all you winter folks out there, ride safe and tell us if this actually works in your environment.